Finally, use the subnet mask to determine the 4 network numbers you will use. We've completed the first network on screen for you. You'll complete the other 3 tables in 2 stages. First, fill in the last octet binary number for each network number. Type into the tables to replace each set of red question marks with the correct binary number. Remember that the network portion of the address should increase by 1 for each new network. Finally, use the subnet mask to determine the 4 network numbers you will use. We've completed the first network on screen for you. You'll complete the other 3 tables in 2 stages. First, fill in the last octet binary number for each network number. Type into the tables to replace each set of red question marks with the correct binary number. Remember that the network portion of the address should increase by 1 for. At this point, you might be asking yourself, how does a company go about getting an IP network address? From the very early days of the Internet, IP network address assignments was centrally controlled to ensure that no 2 networks would ever try to use the same IP network address. In the early 1980s, Jon Postel, an Internet pioneer, voluntarily maintained a list of assigned network addresses, supposedly in a paper notebook. As the Internet grew, the Internet Assigned Numbers Authority, or IANA, was established to centrally manage the global IP address space. Jon Postel administered addresses for IANA for years and allocated addresses to any organization or company that filled out a simple request. As the Internet expanded across the world and addresses started to become depleted, it quickly became clear one central organization could not administer all addresses. In the early 1990s, 3 regional Internet registries, or RIRs, were formed to work with the IANA and administer IP address allocation regionally. As time went on, 2 additional RIRs were added. Finally, in 1998, the Internet Corporation for Assigned Names and Numbers, or ICANN, was formed to be responsible for all IP address assignment and domain name registration. This nonprofit public benefit corporation assumed control of IANA and now coordinates the allocation and assignment of IP addresses and domain names. ICANN allocates IPv4 and IPv6 address blocks in a hierarchical manner to the 5 RIRs. These RIRs then allocate blocks of addresses to national Internet registries and local Internet registries. Internet service providers, or ISPs, depending on their size and reach, obtain their address space from one of these registries. Companies or organizations obtain their IP addresses from their ISPs. Some IP addresses are reserved for specific uses. For example, the private IP address ranges shown on screen can be used within a company's network, but cannot be used on the Internet. Companies are free to use IP addresses out of the private address space within their internal network, which is also known as an intranet, a term you're probably familiar with. Companies must not use these networks outside their intranet, because these same private addresses are used by many other companies as well as home networks. A network host, such as a PC or a workstation, has a loopback interface, which is a virtual software interface not associated with or connected to any hardware that a device uses to send a message back to itself. It is commonly used for troubleshooting and network testing. The IP address 127.0.0.1 is used as the loopback interface's IP address. A loopback interface has several uses. A PC can communicate with a local server without an actual network connection, so it's useful for testing services without exposing them to the security risks of accessing them through the network. A device, such as a PC, might have a web server running on it. The same PC might want to communicate with the web server directly. In this case, the PC uses its loopback address in the URL to communicate with the local web server. Multicast IP addresses are similar to multicast MAC addresses, something we've discussed earlier in the course. Like multicast MAC addresses, devices use multicast IP addresses to send the same data to a specific group of devices. Routing protocols, streaming media services, and internet television or IPTV often use IP multicasting. Now that we understand IP addressing and subnet masking, let's combine this knowledge with the material we've learned earlier in the course. Examine the network map on screen. It should look very familiar. We have simply replaced the simple network number .host number addresses with actual IP addresses. Notice that we're using IP addresses from the private address space. For simplicity, we'll continue to use the abbreviated MAC addresses. So, let's use our new understanding and see what happens when PC 192.168.1.2 wants to send data to 192.168.1.8. We'll zoom in on the first network to get a better look at what is happening. First, the PC needs to know if the destination address is on the same network. It uses the network's prefix length to determine its own network number and the network number for the destination address. In this case, they are on the same network, so the two PCs can communicate directly without the help of a router, which is also known as direct routing. Because the PCs are on the same network, the sending PC needs to determine the destination PC's MAC address, so it sends out an Address Resolution Protocol or ARP request to every device on the same network. Notice that the router does not forward Layer 2 broadcast frames. Only the device with the requested IP address replies with its MAC address using Layer 2 unicast addresses. Now the two PCs can communicate directly. A router wasn't even involved in the process. Now let's see how data flows from a PC on one network to a PC on a different network. In this example, PC 192.168.1.2 wants to send data to PC 192.168.3.2. Again, we'll start by zooming in on the first network. Once again, the PC must first determine if the destination PC is on the same network by using its network mask to extract the network number from the destination IP address. This time, the two PCs are on different networks, so a router is needed to forward the data along to the final destination. This process is known as indirect routing. Instead of sending the data directly to its final destination, the PC encapsulates the packet in a frame addressed to its default gateway. If the PC doesn't know the router's MAC address, it sends out an ARP request. Once it learns the router's MAC address, it sends the data to the router for further processing. As we saw previously, the switch uses a MAC address table to forward data. However, because our main focus is on IP addressing and routers in this section, we won't show the details of switch forwarding anymore. When the router receives the frame, it first examines the destination MAC address. If it is the router's MAC address, the router strips off the Layer 2 frame and looks at the destination IP address. It then looks in its routing table to find a network matching this destination IP address. Earlier, we learned that routers use routing tables to determine the best path to a destination network and forward packets toward that destination. The routing table contains all destination network numbers known to the router and how to reach them. Note that in this network, the router only keeps track of network numbers, not individual host addresses. Routers use static routes and dynamic routing protocols such as the Open Shortest Path First or OSPF protocol, or the Intermediate System to Intermediate System or ISIS protocol to learn about remote networks and build their routing tables. The details of these protocols are beyond the scope of this course. Each entry in the routing table includes the destination network number and prefix length, the next hop along the way to the destination network, and which port or interface on the router should be used to reach the next hop. The next hop either indicates that the destination network is directly connected to the router or provides the IP address of another router on a directly connected network. When a router receives a packet, the router uses the routing table to make intelligent decisions on where to send the packet next. While it isn't shown in the example currently on screen, in many cases a destination IP address might match multiple entries in the routing table, each with a different prefix length. When that situation occurs, routers always look for the best match for the destination IP address. The best match is the match with the longest prefix length, because it is the route with the most bits matching. We'll look at longest match routing in more detail in the next section. Here's a chance for you to perform some of the actions of a router. First, find the best match for this packet's destination IP address in the routing table. Click the row in the table that best matches the destination IP address. When you have the answer, now let's return to our discussion about longest match routing. Earlier, we used the postal analogy to describe how a letter gets to its final destination. We learned that during the routing process, post offices use more and more of the postal code to make a routing decision as the letter gets closer to its final destination. The same is true of IP routing. Let's see this process in action using Acme Company's new manufacturing location. Remember that the manufacturing location was assigned the 192.168.3.0/24 address range, which was then divided into several subnets. Let's say that PC 192.168.1.5 needs to send data to PC 192.168.3.36. When the packet arrives at router A, the router performs a longest match route lookup and sends the packet to router B. Notice that router A's routing table does not contain the different subnet numbers actually in use at the manufacturing location. In fact, router A doesn't even need to know that the 192.168.3.0/24 address range was subnetted. Instead, it simply has the address range allocated to the location or a summary route. Route summarization or route aggregation combines a group of network numbers into a single route. Route aggregation makes routing traffic across the network and the internet much more efficient as there are fewer routes in the routing table and fewer routes to advertise. As a packet gets closer to its destination, the routing table entries get more specific. Much as the post office uses more of the postal code the closer a letter gets to its destination. This way, routers don't have to keep track of every destination network or route in its routing table, which would slow down routing significantly. Routers always use the longest match available to forward traffic. In this example, the destination IP address is 192.168.3.36. Although the first and fourth routing entries both match this destination, the router uses the fourth entry to forward the packet because it is the longest match. Host 192.168.3.36 is on the network 192.168.3.32. It might not be so obvious why the first routing table entry matches the destination. Once again, it is much clearer if we view this example in binary and compare the network portion of each address. Our destination address matches routing table entry number 1 with a 16-bit prefix length. Notice that 192.168.0.0/16 represents the address range 192.168.0.0 through 192.168.255.255. And while the destination does fall in this range, the router will try to find a better match using more bits. This address range, which is an example of a CIDR SuperNet, is actually the combination of many other address ranges that are located at corporate headquarters, such as 192.168.1.0/24, or other locations that the manufacturing location doesn't even know or need to know about, such as 192.168.5.0 or 192.168.10.0. Supernetting alleviates some of the issues with the original IP addressing scheme by allowing multiple networks' address ranges to be combined, either to create a single larger network or just for route aggregation to keep the Internet routing table or any routing table from growing too large. We can see that the destination address does not match entry number 2, which has a 30-bit prefix length. Several bits in the network portion of the address do not match. Nor does it match entry number 3, because the last bit of the network portion of the address does not match. However, it does match entry number 4 with a 27-bit prefix length. It does not match entry number 5 because the last 2 bits do not match. Out of the 2 matches we found, entry number 4 is the longest, most specific match for our destination address. Finally, before we leave the subject of IP addressing, let's take a look at one of the challenges that packets face when they traverse different types of networks. IP's main responsibility is to deliver packets between devices. Remember that a Layer 3 or IP packet is encapsulated in a Layer 2 frame. But before a packet can be encapsulated in a Layer 2 frame, a device needs to make sure that the packet is small enough to fit into the Layer 2's frame size. As we've seen, different Layer 2 technologies have different frame formats. Each data link technology, such as Ethernet or FDDI, has a fixed upper limit on the size of a packet that can be sent in a single frame. This limit is known as the Maximum Transmission Unit, or MTU. Different data link technologies have different MTU sizes.